All right. Good morning, good afternoon, good evening, good night, depending on when you are watching this video. We are going to work through lecture set number 7 from S151. This lecture set is our first lecture set on performing statistical inference. We're going to cover a number of topics in this set. We're going to define the point estimate to start. Then we will discuss effectively how we can account for sampling error when using a point estimate. This is done via a confidence interval. We will look at two examples of confidence intervals. One when we have population standard deviation or population variance, and one when we don't. These are the two sort of major criteria that we have to consider when we are deciding what type of interval to build. We will also talk about how to compute sample size to control for sampling error. So the first definition is that of the point estimate. So recall that statistical inference effectively means or is the practice of making a statement about a population parameter from a statistic. In this course, we will most often or almost exclusively be talking about a population mean or combinations of population means. So that is, we have a population that we want to make a statement about. What we more specifically, when we make this statement, we want to say something about the parameter mu, the mean of the population. So we want to use our sample to say something about the population mean. Now, the first thing that we would do when we want to make a statement about the population mean is we would compute what is called a point estimate of the mean, of the population mean, more specifically. The logical choice for the point estimate of the population mean is the sample mean. So most often, we will use X bar, the sample mean, to make a statement about mu, the population mean. In general, we can say that the sample value that is analogous to the population parameter is a good point estimate, or is the typical point estimate. It might not actually be good depending on the situation you're in. So what I mean is, for example, the sample standard deviation is a point estimate for the population standard deviation most of the time. The sample variance is a logical choice for a point estimate of the population variance. The sample median would be a good choice for a point estimate of a population median, etc. Okay, now we know or we assume that associated with every sample is sampling error because the sample is a subset of the population. So again, what I mean is most often we are working with a collection of values that have been taken from the population, but we do not have access to all of the population values. As a result, we assume that there is some error associated with that sample. When we compute a point estimate from the sample, there's therefore going to be some error associated with that point estimate. So we would like to effectively control for or incorporate that error, that sampling error, into our estimation, into the inference. One way of doing that is computing what is called a confidence interval. So a confidence interval takes a point estimate and adds and subtracts some value, which we call the margin of error, to that point estimate. And the idea is that this margin of error represents that sampling error. Now, when we are estimating a population mean, we are adding and subtracting to the point estimate of the population mean X bar. So here, you can see the general form of a confidence interval. Every confidence interval has this form: point estimate minus margin of error to the point estimate plus the margin of error. What we have to learn how to do in this set, or maybe you will say, or maybe I could say the main thing that we're going to learn how to do in this set is construct or compute the margin of error such that we can then construct the confidence interval. In general, there are three steps to building a confidence interval, or there are three things we need. We need the point estimate, which we can compute. We've actually already learned how to compute x bar. It's the sample mean. We need the margin of error, so we have to learn how to compute that. And then we need what is called the confidence level, which is usually actually just specified. So that's not something that we have to compute. After we construct the confidence interval, so after we perform our calculation, we have to conclude by interpreting that interval. When we interpret a confidence interval, we have effectively you could call it like a stock definition. So a definition that we always use that can be tailored to the situation at hand. So the general statement is shown on this slide. We are some percentage confident. Note the word confident here. Okay. That word is very important. We are some percent confident that the population mean is between the lower bound and the upper bound. So when we are applying this statement to practical problems, it will read something like, we are 95% confident that the population mean is between -2 and +4, for example. So the lower bound and the upper bound portion will be replaced by numbers, and the population mean will actually be replaced by a direct statement about what we are measuring. So, for example, the mean shoe size of all undergraduate students is between 6 and 12 feet or inches, something like this. All right, now this word confident. I mentioned that this word is very important. I even highlighted it. The word confident has a very specific meaning in the context of the interval. So this word represents the idea of repeated sampling. Now, when we construct confidence intervals, we are usually only working with one sample. So the situation or the scenario that we will find ourselves in is one where we have defined a population. So, all McEwen students are the population. We have a variable, shoe size. So we are measuring shoe size of all McEwen students. And we only collect one sample, but we interpret the confidence interval from that one sample as if we repeatedly sampled from the population. So that one sample is a representation or a realization of an infinite number of samples, and we interpret the interval in the context of that. And we interpret the interval in the context or with the understanding that we could compute an infinite number of confidence intervals. Okay, so the word confident should always be in the conclusion. It is different to say we are 95% sure than we are 95% confident. If we interpret the interval using the word sure or any indication of certainty, that's incorrect. We want to make sure that we are conveying that given we can repeatedly sample, we are confident or we have evidence that the population mean of whatever we're measuring can be between these two values that we calculate. Okay, so I'm going to try to illustrate this idea using the following display. So let's suppose that we have some population that we are studying. So this uh, elliptical object here represents the population. Okay. Now in this illustration, so we collect So we collect 20 samples from the population. So from that circular object, we have collected 20 samples. And those 20 samples are represented by or are used to compute the confidence intervals that are shown here. Okay, so we have this population, we've collected 20 samples, and then from the 20 samples, we compute 20 95% confidence intervals. Okay, so CI or CIs in statement number 2 stands for confidence intervals. So again, the scenario is we have this population. We collect 20 samples from this population for illustrative purposes. Usually we will only have one. And then we compute a confidence interval. More specifically, we compute a 95% confidence interval from each sample. So these horizontal lines that are shown on the plot, those are the confidence intervals. They have a lower bound. So this is the lower bound for each one, the endpoint, and they have an upper bound. So every confidence interval ranges from its lower bound to its upper bound. Okay. So this is the confidence interval for sample 1. This is the confidence interval for sample 2. This is the confidence interval for sample 4, etc. So we have 20 confidence intervals, one for each of the samples that we have taken. Again, we will usually only work with one sample, but this is just for illustration. This vertical line here is mu, which is the population mean. Okay. Now, what do we notice when we look at this closely? So I'm going to just make a mark here. The first confidence interval crosses mu. So that means it contains mu. So in this context, again, our goal is to make a statement about mu. We want to say something about the population mean. So we collected a sample, or in the case of sample 1, we have sample 1. We construct a confidence interval. That confidence interval actually contains mu. So that's good. This means that when we interpret the interval, we are actually given a range that covers the true value. This is true for the second interval, for the third interval, but it's not true for the fourth. Okay. Then it's true for the fifth, the sixth, and then all of the remaining intervals in this illustration. So what is this telling us? This is telling us that, again, given that we don't actually know what mu is in practice. So in practice, we have a population, we have a variable. We want to know, or we want to make a statement about the population mean, but we don't know what the value is. So we collect a sample, we compute a confidence interval, and then we use the confidence interval to make a statement about the population mean. That interval might contain the mean, or it may not. And more specifically, the interval will either contain the mean or it will not. It's a binary problem. What complicates this is we don't actually know if the interval that we computed from the sample that we have is going to contain the mean. There's no way to know because we don't actually know what the mean is in practice. So that word confident is reflecting the idea that, again, across repeated samples, we are expecting to cover the mean that percentage of the time. Okay, so for example, here in this illustration, we have 20 intervals. 19 of the 20 capture the mean. That is, they cross the population mean. one of the 20 does not. So that is 95% of the intervals cover the mean, 5% do not. So when we interpret the individual interval, it's in the context of this idea, but across infinite numbers of samples. Okay, so we could say something like, okay, we don't know which interval contains mu, but we expect in this case 95% of the CIs to contain mu. Okay. So once again, the main thing that I'm trying to communicate here is in practice, we build one confidence interval because we usually are working with one sample. We don't actually know if that sample is going to produce a confidence interval that will contain the population mean. But what we assume is that if we were to repeatedly sample over and over and over again from the population, 95% or whatever percentage, whatever confidence level is selected, that percentage of the time, the intervals will cover the true mean or will cover the population mean. Right? So that's the main takeaway from this. And again, this is why that word confident is so important because behind that word is a very specific and a very important acknowledgement of how this process works. All right, so now we're going to look at some examples of actually how to compute this thing and then see interpretation in the context of the different problems that we're studying. All right, so here we have the following values are a sample of 10 scores from a competency test for all first-year university students. Okay, so part A, give the population. Notice actually part A and part B, both of these questions, these are like sort of throwback questions, if you will. These are just asking you to define population. This was one of the very first things we did in this course. Define the variable. One of the early things we did in this course, maybe the fourth or fifth definition that we looked at. So these initial definitions are still being used here. We have to know what we're studying. We have to be able to communicate what it is that we are talking about. We have to give some acknowledgement to what it is we actually want to know. What is it that we want to study? Right? So here, what is the population? Well, that's just all first year university students. Okay. What is the variable? So what are we measuring? Competency score. Okay. So we are measuring, our variable is the competency score of all first year university students at some university. It doesn't strictly state what it is, but the point is that we are measuring this competency score for first year students. And we're going to use this idea when we interpret the interval. Okay, part C. Now, give the point estimate. Just as a note, point estimate is typically something that students get hung up on. I have been asked every semester that I've taught multiple times what a point estimate is when students get to the assignment. The point estimate is a statistic. It is usually the statistic that shares the name of the population parameter that you are trying to measure. So in part C, compute point estimates for mu, should just be compute A. Compute a point estimate for mu if the sum of xi is 1083. All right, so we want to compute a point estimate for mu. The logical point estimate for mu is the sample mean. The sample mean is the sum of the xi divided by little n. So here we have x bar is the logical point estimate for mu. Okay. X bar is the sum from I equals 1 to n of xi divided by little n, which is 1083 divided by 10, which is 108.3. Okay. And so once again, the point estimate is a statistic, a value from the sample. It's usually the value from the sample that has the same name as the population value. So the sample mean is a point estimate for the population mean, for example. Sample standard deviation, point estimate for population standard deviation. Point estimate means value, number, a single value estimate, right? Okay, D asks us to compute and interpret a 95% confidence interval for mu if the margin of error is 12.396. So every confidence interval is the point estimate plus or minus the margin of error. Okay. So every confidence interval has this form. So here we have X bar plus or minus the margin of error. So we have 108.3 plus or minus 12.396. Okay, so this is 108.3 minus 12.396 to 108.3 plus 12.396. So notice that the plus minus means subtract and add. And we usually subtract first and add second. So the intervals are typically read smallest number to largest number. So then we would have, as a result, 95.904 to 120.696. Okay. And then we're asked to interpret this. So remember, the stock interpretation is that we are some percentage confident that the population mean is between the lower bound and the upper bound. So in this question, our population mean represents the population competency score of all first-year university students. And we constructed 95%, or rather, we constructed a 95% confidence interval. This is what the question stated. And once again, confidence level is always going to be stated. You will be told to construct a 90% interval or a 95% interval or a 99% interval. Just depends on the situation that you're in. So here we would start with, we are 95% confident. Okay? So basically every single interpretation starts with that first phrase. We are percentage confident, and that percentage can change depending on the problem. Now we state what we're measuring. We are 95% confident that the population mean competency score of first year university students is between 95.904 and 120.696. Okay. So that's an example of how the phrasing of the interpretation will be done. And every interval basically has the exact same interpretation. It's just that you change the mean. Like, what is it that you're talking about? What is the variable you are measuring? The bounds are going to change and the percentage is going to change. But that structure is consistent across all intervals. So we are 95% confident that the population mean competency score of first-year university students is between 95.904 and 120.696. Okay, the last question asks, if k equals 1,000, 95% intervals were constructed for mu, how many should contain mu? So remember that we expect 95% of the intervals constructed to contain the population mean. So here we expect 1,000 times 0.95 equals 950 CIs to contain mu. Okay. So if we construct 1,000 confidence intervals for the same population mean, so we take 1,000 samples of the same size from the same population, we construct a 95% confidence interval for every single sample. So we have 1,000 sample or 1,000 confidence intervals. We expect 95% of those, so 950, to contain the population mean. All right. Okay, so in this illustration, we are given the margin of error. This is very uncommon. Most of the time, you will be expected to compute the margin of error. So now what we're going to do is learn how to do that. There are two scenarios that we are going to consider when computing the margin of error. The first scenario is when sigma, the population standard deviation, is known. So when the population standard deviation is known, the margin of error for the confidence interval is given here. Okay, so this part is the margin of error. Right? Now, again, this is only true when we know sigma, when we are given the population standard deviation. Notice that the margin of error is a z-score, z subscript alpha over 2, times sigma divided by the square root of n. Recall that sigma divided by the square root of n is the standard deviation of the sampling distribution of the sample mean. So we are actually incorporating the results for the sampling distribution of the sample mean into our confidence interval. You might recall that I described how the standard deviation of the sample means, sigma subscript x bar, represents the sampling error. So we are incorporating this representation of the sampling error into our margin of error. And that gives us equation 1. So this equation is only valid when we know sigma. And basically now what we are able to do is construct margins of error for varying confidence levels given any sample information, as long as we have sigma. Now, the other thing that's very important is we have some evidence that X bar is normal. So we can only use the z-score based approach if the estimate, X bar in this case, is normally distributed. Same logic that we had before. We can't use the standard normal curve to find probabilities if the variable we are studying is not normal. Here, we cannot use this interval, the one given in equation 1, if X bar is not normal. So in general, when we are constructing a confidence interval, if we know the population standard deviation, we must also be able to say that we used simple random sampling. So we want the sample to be representative. We must also be able to say that X bar is approximately normal, which means that we either collected from a normal population or we have enough observations, 30 or more, such that we can apply the central limit theorem. And then again, like I already said, we must have sigma. Given those things are true, we can then follow a three-step process. Find the z-score that we need given the confidence level, compute the margin of error and then the confidence interval, and then interpret this interval. So for example, returning to the illustration that we had just looked at. So we have a simple random sample of 10 scores from a competency score or from a competency test of all first-year students, right? Okay, so in this illustration, we are told to construct or compute and interpret a 95% confidence interval if sigma equals 20. So notice here, we are given sigma. Okay? We have to assume, and then we are told to assume that competency score is normal. So this is saying your population or the variable that you are studying is normally distributed. So if the variable from the population is normal, X bar is also normal. We know this is true because of the properties of the sampling distribution that we discussed in lecture set 6. So now we have SRS, which is our first assumption, right? So that's given here. We have sigma here, and we are told to assume normality. So these are the three criteria that were mentioned on the previous slide. And typically, every confidence interval problem starts by checking that these criteria hold. Now, in step 1, we find our z-score. So the confidence level here is 95%. The confidence level is defined as 1 minus alpha. So that is, we can say 0.95 is equal to 1 minus alpha. Okay, so alpha is 0.05. Right, so alpha is the complement of the confidence level and as a decimal, so not as a percentage. So the z-score, which is shown below here, which I will write over here, is z subscript alpha over 2, which is z subscript 0.05 divided by 2, which is z subscript 0.025. So notice that we are using the z-score notation that we discussed in lecture set number 5. Okay, so we are basically defining percentiles of the standard normal curve. So in this case, we have z subscript 0.025, which means that this is a size 0.025. Okay, so basically step 1 is using that second foundational technique from the standard normal table, which is the technique of finding percentiles. So given an area under the curve, find the associated z-score. So this isn't actually an example that we looked at in lecture set 5. So we have 0.975 of the area to the left. If we look up 0.975 in the normal table, we will find that the z-score associated with it is 1.96. Okay, so step 1 is just utilizing that second foundational technique, finding z-scores given area under the curve. Now on step 2, we just plug into our equation. So the equation is x bar plus or minus z alpha over 2 multiplied by sigma over the square root of n. So we have 108.3 from example 1 plus or minus 1.96 multiplied by 20 over the square root of 10, right? So we have 10 observations in the data set. You can count those from the top of the slide. We are told sigma is 20. We just found that z is 1.96, and in example 1, we computed x bar. Right? Now, if we multiply 1.96 times 20 over the square root of 10. We get 108.3 plus or minus 12.396. So now we can see where the value 12.396 came from in example 1 from this lecture set. Then we add and subtract that value, and that gives us the confidence interval we computed in example 1, and then we have the same interpretation that we already discussed. So the process of computing the interval is not terribly difficult. We have three assumptions that we want to check: that a simple random sample was collected, that X bar is normal, and that can be because the population variable is normal or because we have a big enough sample size that the CLT can be used. And then we want to check if sigma is known. If sigma is known, it means that we're going to be using a z-score. The z-score is found using is a percentile of the normal distribution. So we're using the technique from lecture set 5, the second foundational technique, in step 1 of the interval construction. Then on step 2, we actually just plug into our equation, we build the interval, and then step 3, we interpret that interval. All right. Now, couple of things to note about this particular interval. This first part would actually be true for any confidence interval as long as n is fixed, or sorry, as long as we fix one of the values, either the confidence level or the sample size. So for example, if we fix confidence level and we increase sample size, the interval is going to become more accurate. That means that the bounds are going to be closer together. Similarly, if we fix the sample size and on the other hand, if we fix the sample size and we increase the confidence level, the interval is going to become wider, meaning the bounds are going to get further apart. So these first two examples are effectively saying that for the same confidence level, increasing sample size will return a tighter interval, which is to be expected. This is basically saying we have a reduction in the error or in the margin of error associated with this confidence level. On the other hand, if we fix little n and we say, well, I'm just going to max out my confidence level, that's going to come at a decrease of accuracy, which is why we have this trade-off between confidence level and sample size. The instinct would be always to take the maximum confidence level that is given to you, because you're going to be the most confident at the highest confidence level. But for a fixed sample or for a smaller sample size, you're going to produce a very wide interval. So you're going to have a much bigger space that you are making your statement within. And at some point that might not be useful. Right, so to just wrap our minds around this idea of accuracy, let's suppose that for that previous illustration, we have our 95% interval, 95.9 to 120.7. So I've just rounded to 2 decimal places here. This is the same interval we just computed. And then we have the 90% interval, which is 97.9 to 118.7. So what we can see is that for a fixed sample size of 10, if the 95% interval, which is a higher confidence level than the 90%, is a wider interval. Right? And we can actually visualize this really easily. So if we draw a vertical